Alrighty, let's get started. So last class, we studied some probability, and today we are going to use said probability to do Bayesian filtering, right? So, oh no, forgot my clicker thing. It's okay. So we covered robot design. Today we're going to get into the details of how to build Bayesian filters out of the building blocks of probability. So there's going to be no extra knowledge needed, just what we covered in probability. Some logistics. Project 1 is out. We created the repos for you after some drama. But let us know if there's any trouble. Car pickup is tomorrow and day after. There's also UW CSE is trying to have a photo shoot. If any about this class, if any of you want to be in a photo shoot, it's tomorrow morning at 11:30. Come by the lab. You'll be in the UW CSE videos. It'd be great. Cool. Any other logistical concerns, questions? Anyone has problems with access or anything else? Yeah? No? Okay. So let's start with weird. That's definitely not supposed to show the answer. Sorry. Aha. But now it doesn't even show you the. Oh, there you go. Jesus Christ. um, Whatever. Fuck it. Just scan it. Put your participation down. It's okay. This is not a technology is not cooperating today. Give me 10 more seconds. Okay, good to move on. Everyone got it? All right, let's keep going. Um, okay, so what we're going to try and understand today is what it means to estimate state, right? So we want to figure out how to get an estimate of state given past measurements and actions, right? And so last time we discussed what is state. State is like the minimum set of things that are changing and allow you to make decisions. Our state estimation problem is trying to estimate what is P of xt given z1 to t and u1 to t, right? And so we're gonna try and estimate a belief of what the current state is given past measurements and past actions. We're not gonna have access to past states. No one ever tells you the state. You just get measured. And so your belief is the probability over each possible state given your history. And you're trying to estimate this thing called a posterior. Your posterior is P of xt given u1 to t, z1 to t. Okay? And so different algorithms are just going to be different instantiations of solving this problem. So that's what we're going to try and do. Just as a recap, fundamental axioms of probability. Probabilities lie between 0 and 1. They sum up to 1. And A union B is A plus B minus A intersection B. Right? Joint and conditional probabilities. If two things are independent, their joint probability is the product of their individual probabilities. When you have a joint, you can always write it as P of x given y times P of y, or P of y given x times P of x. And if x and y are independent, then P of x given y is the same as P of x, because y doesn't affect x. Okay? And finally, probabilities always sum up to 1 or integrate to 1. If you have a joint distribution, if you sum up over one of the variables, it gets marginalized out, so you just remove it. So sum of P of xy with respect to y is P of x. And that's it. Right? That's all that we really need to know. And from there, you can derive Bayes' rule, right? So the way you get Bayes' rule is you can show that P of X comma Y can be expanded two different ways. X given Y times P of Y, and Y given X times P of X. You just transpose one of the terms to get Bayes' rule. The Bayes' rule says P of X given Y is P of Y given X times P of X divided by P of Y, right? That's all the Bayes' rule is. This is Bayes. Okay. Yes? Everyone feel ready to do filter? Okay, I guess you don't know what filtering is. So, but Andy is thumbs up to me. So let's keep going. So we start with the probability recap. Let's try to go over Bayesian filtering. We'll do some examples. And then if we have time, we'll get to motion models. So let's try and represent this problem with a graphical, representation. So let's say your state at time t minus 1 was xt minus 1. You're going to have an action ut that's going to lead to a state xt. You're going to get a measurement zt, and then you'll get another action that'll lead to state xt plus 1. You'll get another measurement, and this whole process repeats, right? And so your assumption is that your robot will receive a stream of measurements and actions, and you're only going to get one measurement, an action per time step. And so if you have multiple measurements, they're all going to be kind of within that same ZT. Like for instance, you have multiple sensors. For now, we're going to keep them in the same ZT. You can derive the algorithm with multiple measurements. But this is going to be the assumption. But we kind of go through the world sequentially. You say, you're at some state xt minus 1, you don't know it, but you take an action, it takes you to xt, you get a measurement zt, take an action, get a measurement, repeat. Right? So the notation we're going to use is that xt minus 1 and ut take you to xt, you get a measurement zt, you repeat. Yeah? Okay. So what is Bayesian filtering? Bayesian filtering is trying to get p of xt given z in the past and u in the past, right? And so this is not actually fully correct. Ignore that. You don't actually know xt minus 1, right? So you only know the past observations and past actions. Yeah. Now, the problem with this setup is that it's intractable, right? Why is it intractable? Guesses. Like it's impractical to compute computation. Yeah. You have a ton of states. Yeah. So you have a ton of states. So the number of states might be uncountable, which will make it hard. So that's one for sure. What else might make it intractable? Yep. A great point. Yeah, you were doing, it's an inherently continuous process. We're discretizing it. That is definitely a problem. So you'll have accumulating error more when you discretize tiny. So that's a great point. Any other thoughts? Yeah.
If we're considering all the houses, there might be a lot of stuff that's irrelevant.
That's right. Yeah, there's a lot of stuff that's irrelevant, and the number of combinations of like past UTs and ZTs throughout the whole history is exponentially many, right? So there's like K possibilities here, K possibilities here, K possibilities here, and it just becomes exponential, right? And so the number of possibilities you have to keep track of to kind of solve this problem becomes too large. So all of the three issues that you mentioned are issues, yeah? Well, it becomes computationally intractable unless you have like infinitely fine discretization. Right. So if you're talking about intractability, then it becomes intractable. Okay. Cool. So this process by itself is intractable. So what we're going to try and do is we're going to use an assumption by this guy Markov. Has anyone heard of the Markov assumption? Yes, kind of. Okay, so all that the Markov assumption says is that the past is independent of the future conditioned on the present. Right, so that means that I don't need to know all of my history to make decisions about the future. I just need to know my current state, right? So what it says is that if I am looking at like xt minus 1 and xt plus 1, they're independent given xt, right? And so all that the Markovian assumption is saying is that your current state xt is sufficient to make decisions about the future. You don't need to have your history. And so all of this like exponential thing that I was talking about, where you have to like have exponentially large history, it kind of goes away because you can forget your history as long as you have your current state, right? And so what's going to make this tractable is the Markov assumption. And so when you write out the Markov assumption mathematically, you can write it like this, which says that P of xt conditioned on history, right? You can drop all the history except for the past state and the past action, right? And so if you like kind of look at it graphically, you can see that like basically xt only depends on its parents, right? And so once you condition on the parents, it like separates it from everything else in the past. So one way of thinking about how to enforce the Markov property is like look at the graph, look at xt. When you condition it on its parents, it's independent of everything else in the past, right? And so what that means is that I only need to have a table of this size rather than a table that is exponentially large, right? So it's an assumption, but it's an assumption that allows me to have a table that just matches the past state and the action to a next state. I don't have to have a table of all of the past history, right? And so that's the first part of the Markov assumption. The second part of the Markov assumption says that the likelihood of a measurement given X, U, and history just depends on the current state. That's it, saying like, if I'm a robot, I'm going to get a sensor reading. It only depends on my current state. It does not depend on my history, right? And so what it's saying is that XD is a sufficient statistic for history. Yeah. And so Markov is going to make our life easy because it's going to be easy to represent this and easy to represent this. The problems of continuous and those kinds of things still hold, and we'll try to address them, but at least it deals with the history expanding exponential. Yeah. Yes, no, maybe. Cool. All right. So that's what the Markov assumption is. And so we're going to have these two functions. So if you remember here, we have P of xt given ut and xt minus 1 and P of zt given xt. This one will be called a state transition dynamics, a motion model, dynamics model, a world model, and all of those are kind of the same. But basically, it's saying it's something that takes in your past state and your current action and gives you the next state. Right? So xt minus 1 and ut give you xt, and the model that tells you how state evolves given action is called your state transition probability. Right? Yep.
That the sensor measurements that we're getting are not part of this equation?
Because once you have xt minus 1, that encapsulates everything that you're like, if you're looking at this equation, I'm sorry. If you're looking at this equation, right? This is conditional not on the latest ZT, but on everything in the past. So if once you condition it on the latest ZT, it becomes a little different. But this is just saying like, imagine everything from here on out, like not including this guy. Right? So it's saying that like none of like, let's say the sensor measurement over here, let's call this ZT minus 1, right? All of the information that is in ZT minus 1 is actually stored in XT minus 1. So you don't need ZT minus 1. But it is different for ZT, and we'll cover that. So the indexing is a little tricky. Just be careful on the index. Okay, so our transition dynamics model is going to be xt given xt minus 1 and ut. Our measurement model, our observation model is going to be P of zt given xt. So the first one is telling me how does the world move, right? Like how does the world change given action? And the second one is telling me if I was here, like what is the likelihood I would observe this sensor reading? So it's like if I was here, what is the likelihood I would see this LiDAR reading? Or what is the likelihood that I would get this image, right? It's like telling me how likely is a measurement given a state. Right? So this is your transition model. This is your observation model. Okay. So when does Markov not hold? Right. So we talked about the Markov assumption. It's an assumption. Like what is an example of a situation where Markov doesn't hold? Yep. Yeah, so if you're not measuring, for instance, like if your state doesn't include anything about the tire, then it's not Markov. Yeah. Some other examples are so basically when your state doesn't capture everything about the present, right? Like for instance, if you have like camera images at different time of the day and your state is just like position, how's it going to capture like the difference in images, right? So their state is insufficient. Or if there's things like pedestrians who you're not modeling, right? They might be changing. So like if you ever start getting different sensor readings from the same state, that means you're not Markov, right? Or different sensor reading distributions from the same state because your state doesn't capture enough, right? Or something like gusts of wind that you didn't model, right? So an example that I find useful to think about is like, imagine you're like an egocentric robot that's only looking straight. Like I can't just take my current observations and make decisions on it because there might be something behind me or to the left of me that I missed, right? And so that's not Markov. But we're going to assume that the world is Markov and it is useful for lots of settings. Okay. Or we're going to assume the states are Markov. Okay, so our Bayesian filtering problem is going to say we have measurements, we have actions, we want to estimate belief, and we want to estimate a probability distribution over belief. So we're going to use a Bayes filter. And what a Bayes filter does is going to try and estimate P of xt given u1 to t, z1 to t in terms of previous belief. So you're going to try and do it recursively in terms of previous belief, a measurement model, and a dynamics model. Yeah.
Oh, what do you think the situation for the Markov system?
You include history. Okay. You include more history. Or you expand your state. Good question. So the process of Bayesian filtering is going to be to try and estimate what is our belief over our current state. Recursively using our belief over our past state, a measurement model, and a dynamics model, right? We're just going to try and rearrange these terms to get what we're looking for. And so all that you really need to implement the Bayesian filter is a recursive process using these two things, and you just rearrange them with recursion. Okay, so let's try and work through the Bayesian filter. So essentially the key idea is going to be that you apply the Markov property to get a recursive update. So an update that you can keep repeating, right? So we're going to start with the belief at time step t minus 1. So belief at time step t minus 1, can someone tell me what that is in terms of probabilities? What is belief at xt minus 1? Yeah.
Probability that we're at xt minus 1 given the state and action previously.
So given actions and measurements previously. So yeah, that's good. That's what it's going to be. Your belief at xt minus 1 is going to be p of xt minus 1 given u1 to t minus 1 and z1 to t minus 1, right? And what the first step of the Bayes filter is going to be, it's going to be your prediction step, is it's going to go from this belief at your previous time step to something we're going to call belief bar. Or I call it belief bar, but belief with a bar on top of it, right? And so what belief bar is going to do is it's going to account for one action, but not the next measurement. So it's like you were at xt minus 1, you took a ut, you're going to account for this action, but you're not yet going to account for the next measurement, right? So you're just going to take one action, and it's going to act as if you didn't get a measurement, and you're going to get belief bar, and then you're going to add in the measurement, right? And so the first step of the Bayesian filter is going to be that you're going to start with belief xt minus 1, and you're going to try and propagate forward to get belief bar at xt, which is p of xt given actions 1 to t and z1 to t minus 1, right? So if you look carefully at the indexing here, it's important to look at the indexing. This and this are different. This and this are different, right? So you're going to incorporate ut and you're going to predict xt. Right? So you're going to predict the next state and you're going to take into account the action, but you're not going to take into account the measurement yet. Right? You're just going to take into account action, no measurement. And so the first step of the Bayesian filter, the prediction step, is you're going to try and go from belief at the previous step to belief bar at the next step using just the motion model, just the dynamics model, just something that tells you what is xt given xt minus 1 and ut minus 1. Right? Okay. before I tell you how to get there, any guesses at how to, yeah, go ahead. Mhm.
Your state, the probability distribution. If the belief isn't a concrete.
Yeah.
Position, how would I an action?
So the state is, there is a state in the world, right? This is like my robot is somewhere. I just don't know what it is, right? So I can apply an action, like I can apply torques. I don't know what my state was, and I don't exactly know what my state is going to be, but I can maintain a probability distribution about it. So there exists a state in the world. I just don't exactly know it. Right. So it's like your robot is somewhere, right? But I don't exactly know where it is, but that doesn't preclude me from taking actions with the robots. So in Bayesian filtering, I'm gonna assume that the actions are given to me. Like I'm gonna assume that like someone drives the robot around. The actions are given to me. And so the state exists. I don't exactly know what it is, but my actions are going to change the state, and it's going to change my belief over the state. So the state is an inherent quantity of the world. I just don't know exactly what it is. Does that make sense? So it's like my robot could be anywhere in this region. In reality, it is exactly in one place. But because I don't have exact measurements, I don't know exactly where it is. So I'm going to say like my robot could be somewhere here. That's my belief. I'm going to take an action. And what I want to do is have my belief after that action was taken. So let's say my robot could be somewhere here, and I decided to move left, right? Now my robot will be somewhere here. And so what the prediction step tries to do is it tries to take my previous belief and propagate it to a next belief. But in reality, the state is changing. There's like a true state, but I just don't know it. Right? Does that make sense? It's a great question. Yes. So think about it as like you kind of like this figure kind of illustrates that you kind of know where the car is. You don't exactly know where it is. You're going to take an action, and the action will say, okay, well, the car is now in one of these places. It's not a great model. It has lots of uncertainty, but it's saying that like I don't exactly know where my car is, but I think it's somewhere here. And once I move in this direction, because my model is not perfect, I think it'll be in one of these places. And so you update your belief on where your car is going to be. Does that make sense? So the prediction step is saying, if this was my belief, I took an action, what is my next belief going to be? Yes? Okay. So if that makes sense, any guesses on how do we go from belief at the previous step to belief bar at the next step? Like there's going to be an equation that connects this to this using this. Any guesses? No? Yeah. Bayes rule is not yet. We will good guess though. Yes, we're going to use chain rule. Exactly. And so Bayes rule will come next, but let's use chain rule now. Right. So what we're going to try and do. Sorry, did someone raise their hand and I missed it? Okay. So what we're going to try and do is we're going to use this rule of total probability. Let me first explain it to you intuitively, and then we can work it out, right? Intuitively, you can kind of think of it as, the car could be here, it could be here, it could be here, it could be here. And I have some belief over where all of these things could be. So that is saying that I have like some likelihood that at the previous step, my car was here, 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 or here, right? Now, to know the likelihood that my car is going to be at some state after an action, you're going to take the likelihood that it is at each of those previous states, and then the likelihood that the previous state transitioned to that next state, right? So saying that like, if I want to figure out the likelihood that the car was here, I'm going to take the likelihood that it was here, and then the transition probability of going from here to here when you took that action. And the likelihood that it is here, and then transition probability of going from here to here when I took that action. And likelihood that it is here, and the transition probability of going from here to here when I took that action, I'm going to sum them all up, right? So it's like, maybe my car was here. This is the probability that it's going to be here. Maybe my car was here. This is the probability that's going to be here. And so to get the probability at any state, you take all of the previous states, their probabilities, and then multiply it by the motion model likelihood. Good.
How many like previous states or to track? Okay.
That's a great question. Great question. That's why I've written discrete over here. So in this case, I'm going to assume a countable number of states. And so, so if I have a countable number of states, then you can sum up over all the states, right? So it's kind of like saying, imagine that I could be in any one of these places, and at the next state, I could be at any one of these places, right? So to figure out where I'm going to be here, you have to take each of these, and then their likelihood of mapping to here. You have to sum them up, right? And so you have to sum up over, this sum is actually over all xt minus, right? And so one thing that becomes really hard is as your state becomes continuous, you have to integrate over all xt minus 1. That's hard. And we're gonna make that easier, but that's hard. Good question. But does this intuitively make sense? You're gonna say like, take each of the previous positions and the likelihoods you were there, and then take the likelihood of transitioning into that particular state and sum them up, right? So it's like, I had like 50% chance of being here, and then from here, I had 50% chance of getting here. So I'm going to add in 0.25. And here I had 10% chance of being here, and I had 0 likelihood of transitioning there. So I'm going to add in 0, right? And so you can keep continuing through all the previous states and say likelihood of the previous state times the likelihood of transitioning into a particular next state given an action, and you sum them all up. Does it make sense intuitively? Like, they're all the places I could be. How likely are they to transition to a particular next state? And you have to compute this for every single next state. Okay. Intuitively, it kind of looks like the law of total probability. Let's try and derive it, right? So let's try and derive what we want to get is belief power, right? Belief power is the probability of xt given u1 to t and z1 to t minus 1. Remember, we added one action and we're predicting the next state, but we're not taking the next measurement. So this is not the next measurement, right? Just only the past measurements. So any thoughts on how we're gonna derive this? How do we derive the thing on the top from here? So one way of thinking about it is, whenever you're trying to do this kind of derivation, look at this thing. It does not have an xt minus 1. There's no xt minus 1 in there, right? So how do I get an xt minus 1 into this thing? Yeah.
I guess z is like something that derives from xt minus 1. So if you express z in terms of xt minus 1 and the action that was taken from xt minus 1.
Kind of. That's not exactly what I'm looking for. So let me tell you what I'm looking for. We're going to try and use, if you remember this rule, right? If you sum this up over y, this is going to be equal to x, right? So if you take a joint probability, sum it up over y, you'll eliminate it, right? Which means that you can write this thing as the sum over xt minus 1 of p of xt comma xt minus 1, right? So it's just like, I'm just going to like add in another variable and then sum it out, right? So it's kind of saying like, in this equation, this guy is x, this guy is y, right? And the conditionals remain the same. But the point is that if I have p of xy and I sum up over y, I get p of x, right? And so what I'm going to do is I'm going to introduce an xt minus 1 and sum up over xt minus 1, right? And so if I sum up over xt minus 1, this and this are equivalent. Okay? You can just think of the sum over xt minus 1 eliminates xt minus 1, right? So these are, I added something and I eliminated it, just like a nothing operation. Is there a question? No question. Okay. So does this make sense? I just use this like law of marginal probabilities. If I have a joint, I sum up over one of them, it eliminates it. That's it. Okay. So now I have this thing. How do I simplify that? Yeah.
Well, with the, what is it called, the Markov thing?
Yeah.
You can assume belief xt minus 1 is equivalent to like probability that x, or other way around. No,
Right.
no, yeah. Probability that xt minus 1, and yeah, I don't know how to.
So yeah, no, I got what you're saying. So we're gonna do one step in between. The next step we're gonna do is we're gonna note that it's the chain rule. So we're gonna say that if you have A comma B, you can write that as A given B times B, right? So if you have like a joint probability distributions, like if you have P of A comma B, you can write this as P of A given B times P of B, right? That's what we covered earlier, right? And conditioning just always goes on the right. Don't worry about conditioning. So if you can use the chain rule of probability, how do we split this using the chain rule? Yeah. I want to move the xt minus 1 to the right. Right. So what we're going to do is in this try to use this identity, right? Xt is going to be A, xt minus 1 is going to be B, and all of this conditioning is going to be C, right? And so all we're going to do is we're going to take this joint distribution, write it as P of xt given xt minus 1 and some stuff times P of xt minus 1 given some stuff, right? So you're just going to split the joint into two parts. And then we're going to use what Violet just said. We're going to use the Markov property, right? So you note that like the current state only depends on the previous state of the action, nothing else in the past. That's what Markov says, right? And so then the first term, you can drop all of the conditioning, right? And then the second term is just the belief at the previous state, right? And so what this tells us is that your belief bar incorporating the action is just the previous belief times the likelihood under the motion model summed up over all the previous steps, right? You don't have to do this all the time. It's just useful to know how to manipulate probabilities, right? So whenever you see the final answer have another probability variable, just inject it and sum it out, and you can usually get some stuff with it, right? So whenever you have like xt minus 1 showed up on the right, but it never showed up in the definition of belief bar, just introduce it and sum it up, and you'll kind of get what you're looking for. Okay, so intuitively, belief bar is the sum over each previous state belief times the likelihood of transitioning to the next state given that action. Okay, so this is going to be our motion model step, right? So this is going to say, this was my belief, I moved, now this is my belief, right? I'm going to move, now this is my belief. So is that belief going to get narrower, wider? What's going to happen? Like when I take an action, generally wider. Is there ever a scenario where it gets narrow?
Maybe like for the example, you're like moving into a wall.
That's right. Yeah. So if you go into a wall or you go into like a certain state where you're like reducing uncertainty because it has to do that, then you can narrow. So it's not always getting wider. But if it's like, I'm just moving in free space, there's slip, there's other uncertainty, it's going to keep it free. Good point. Okay. The second step is now, okay, you've moved and now you're going to take a measurement. That's you're going to measure what happened in the world. And so you now want to go from belief bar to belief at the next time step, which is saying that like belief bar is likelihood of xt given previous actions and previous measurements, or it's given previous measurements and actions until the current, right? What you want to do in belief is you also want to include the latest measurement. You also want to include the latest ZT, right? So if you remember our graphical model from earlier, our graphical model, so far we just incorporated this stuff. Now we want to incorporate this guy, right? So going from belief bar to belief is just incorporating the latest ZT. And so what we're going to try and do here is we're going to try and go from belief bar to belief using our measurement model, right? So our measurement model is telling us how likely is a measurement, ZT given XT. We're going to try and use that in order to go from belief bar to belief. The main difference between belief bar and belief is that guy, right? So one is going from 1 to t minus 1, one is going from 1 to t. Yes? Okay. So, Devin, right? So now is when you use Bayes rule, right? And so we're going to try and use Bayes rule to give us the answer. And so what we're going to get is belief, I'm going to first tell you the intuition and then we'll work it out, right? But belief at time step xt is going to be belief bar at time step, belief bar at the state xt multiplied by p of zt given xt, normalized by the sum of that over all possible states, right? And so you can kind of think of it as like, this is what my belief was before I took a measurement. I'm going to weight that belief by the likelihood that I got the measurement that I got given that state. And then I'm going to normalize that over all the states. Okay. And so this is like a simpler way of thinking about it. Just think of this eta as a normalizing constant. Right? Think of it as just something that makes it a proper probability distribution. But you can think of this as like, I believed that I was here, 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 here. Now I want to like take a measurement. My measurement is going to be like the likelihood of getting the measurement that I got. Let's say I shot some laser beams out and I got some measurements, right? The likelihood of receiving that measurement at this state was super high. The likelihood of receiving that measurement at this state was super low. So I'm probably not in these states. I'm probably in these states, okay? And so you can kind of think of it as you're taking the belief, your previous step, belief bar at your previous step. You're weighting it by the likelihood of getting the measurement that you got using your measurement model. And then you're normalizing it to be a proper probability distribution because it has to sum up to 1. It has to be a probability. And so essentially what you're doing is you're refining, this is called the refinement step or the correction step, because you're refining your belief. You're saying, hey, when I took this thing, I spread out my belief a lot. I didn't know exactly where I was, but I took this measurement and my laser beams, like if I was in free space here, my laser beams would not come back, right? So it's probably not this, this, or this. It's probably one of these two, because that kind of matches the measurement. So you can kind of think of it as like I took a measurement and I matched it template-wise to different states. You have a table of different states and what the measurements are likely to be. And then you match the measurement you got with the measurement you expect to get and reweight your states accordingly, right? And so you can kind of think of this as like taking a measurement, weighting your belief by that measurement, and then normalizing to be a probability distribution. Does that make sense? Yes.
So, like single dimension variables like scalars, right? Like what if we eventually introduce multiple like different sensors and try to like use them?
You have to integrate over all of those sensors. Yeah, like so like for instance, you're gonna but like for instance, your P of zt given xt is going to be a scalar, and your belief bar is going to be a scalar, right? So like you're trying to get a probability, right? So this is going to be a scalar, this is going to be a scalar. What's going to happen is that this sum is going to be over like a vector spaced xt. Right? So it's like not going to be 10 different outcomes. It's going to be sum over x, sum over y, sum over z, right? So that's what gets nasty. And then you have to compute this for many, 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 many things, right? But great question. So what happens with vectors? Okay, questions? Go ahead, Andy. Great question. So there's going to be some instantiations that we think about, right? So if you instantiate this discretely, then you like sum it up over all the discrete things that you have. If you instantiate this with these things called particle filters, they basically approximate continuous things with discrete things, and you sum it up over all your particles, which is going to be a lot. If you do it continuously, it's intractable because you have an integral in your denominator. Integrals are bad. Integrals in your denominator are catastrophic. Avoid. And so if you're going to have an integral in your denominator, it's going to be intractable. And so this is like the bane of machine learning. You cannot have an integral in your denominator. And so what we're going to do is we're going to try, if zt given xt and the motion model are Gaussian, then it's tractable to compute this. Like you can compute this analytically. It'll simplify to a nice Gaussian. If it's not Gaussian, we will try to make it a Gaussian. We're a very primitive race. We only know Gaussians and how to deal with Gaussians. But yeah. So imagine that as Violet was saying, you have like 100-dimensional space. Right? Imagine you had 100-dimensional space, and each dimension you've discretized 1,000 times. Right? So the number of bins that you have is now 1,000 to the 100. So like that's not storable in memory. right? So if you have 1,000 to the 100 bins, it's just like totally intractable to store in memory. It's totally intractable to do those summations. It just becomes totally memory intractable. Yeah.
So are you saying we store the likelihood of the state versus like the actual, like all the states we think in memory?
So far we've been kind of like dealing with things discretely, right? So here you would have to store, it's kind of like a table whose the number of dimensions of which is the number of states, right? So it's like you'll have a table of the number of states. And so that's what I'm saying. It's like if it's a continuous space, you have to discretize per dimension, then that becomes like ginormous as a table. And so there's different types of approximations you can make, right? So like one of them is to be Gaussian, and then everything is closed form and tractable. And it's a like simple form. If it's not a Gaussian, then what you try to do is you approximate it with particles, which means that you keep like, rather than keeping the whole table, you like choose parts of the table and keep it around. Right. So what a particle filter in some sense is saying that like, rather than having a whole table, a lot of which is empty, just keep around the entries that matter. And that's kind of what we're going to cover next week. Great question. Any other questions before we derive this? No? Okay. Let's derive this. So we're going to try and write belief, which is xt given u1 to t and z1 to t, in terms of belief bar. Belief bar is xt given u1 to t and z1 to t minus 1. And the motion model, or the observation model, which is zt given xt. Right? So we're going to try and write this thingy in terms of these two thingies. Yes? So how do we start? I think we should take Devin's lead here and kind of try to convert it into something that looks like Bayes' rule. Yeah. So the way to kind of convert into something that looks like Bayes' rule is the following. Let's try to separate out z1 to t into z1 to t minus 1 and zt. Okay? It's just like an array. You just take 1 to t minus 1 and separate out the last term. So you can write the belief as xt given u1 to t, z1 to t minus 1, and zt. Those are exactly the same thing. I just separated out the last term. Right? These are like literally the same. I just separate out 1 to t as 1 to t minus 1, and then t. That's all. Okay. Why did I do that? Like what? Like we're trying to convert this into a Bayes rulable form. Right. So good.
Yes, and you can bring the form like the right stuff.
Yeah.
Condition on to be.
Exactly.
Okay.
That's right. That's right. And so now what we're going to try and do is we're going to look at Bayes' rule, right? This is just Bayes' rule. I just added this. Don't get confused by the z. It's just conditioning across everything. I just think of it as something that always lives on the right side of the bar. Z lives on the right side of the bar everywhere, but it's just saying p of y given x is p of x given y times p of y divided by sum of p of x given y times p of y. Right? So that's just Bayes' rule, just with conditioning. Just think of z always as on the right, doesn't matter. But now let's do some pattern matching. So what is y going to be? Yeah. Y is going to be x of t. Great. What is x going to be? X is actually just going to be zt. And then z is going to be all of this stuff. Yeah. So we're just going to do pattern matching. Y is xt, x is zt, and z is all of the previous conditioning. Right? We're just going to apply Bayes' rule. And so what that leads us to is we're going to write here x given y. X, remember x was zt, y was xt. So you're going to have zt given xt and this conditioning times p of y given z. Remember y was xt. I'm just going to write this down. Y is xt, z is y is xt, x is zt, and z is u1 to t minus 1, z1, or u1 to t, z1 to t minus 1. Right? that's what our variables are going to be, right? So if we just do some pattern matching, you can see that like this term is P of X given YZ. This term is P of Y given Z, right? We're just going to directly apply Bayes' rule. So the trick is just you want to separate out ZT and then you want to flip it with Bayes' rule. And so now let's try it. How do we get from here to here? Yeah.
Okay, that's my house rule. So ZT is dependent only on XT.
ZT is only dependent on XT.
Yeah, whereas XT, I mean, you can leave the XT.
Yeah.
ZT parts sufficient of XT.
That's exactly right. So where you get from here is that you can use Markov rule, which says that ZT doesn't depend on the history if you know XT. So ZT just depends on XT. This term in the top is just belief bar. It's XT given U1 to T and Z1 to T minus 1. Belief bar. Right, so this is the same as this. It's saying that this is P of ZT given XT times belief bar divided by the sum of P of ZT given XT times belief bar. Right? So you can kind of think of it as like, take the likelihood of a previous measurement, weighted by the likelihood you got the previous state, weighted by the likelihood you got the measurement at that state, and then normalize it. So the difficult part in any continuous space is like, how do you compute this normalizing factor? Like, this is easy. This is hard. Okay. And so a lot of the difficult parts of this math is just how do you get this sum in continuous large spaces? Okay. Everyone with me so far? So the Bayes filter, all that it does is start with, if you apply a recursive step, you start with some initial belief and you just keep applying this over and over. But you first do a motion model, which means that you take an action and you push your belief forward. You have your previous belief, you push it forward through the motion model, which means that you take your belief multiplied by the motion model, sum it up over all previous states, right? And then you're going to correct. And so correct means you're going to take your belief bar, you're going to weight it by the measurement that you got and the likelihood of that measurement. You're going to normalize it to be a probability distribution. Right, so you can kind of think of this as prediction. It's like taking your current thing and moving it, right? And correction is saying, I'm like uncertain. Let me take a measurement and let me narrow that distribution, right? So as Siddharth was saying, prediction is going to make things wider. Correction is going to make things narrower. Going to go prediction, correction, prediction, correction, prediction, correction. Does it make sense? So all you need to do is, like, everything is tractable if it's discrete. If it's not discrete, hard. And we'll solve it. Does it make sense as a procedure? Go ahead. You have like some hand specified initialization. You like say that it's uniform or something. And then you refine it over time. Any more questions? Okay. It's useful. Bayes filters are used all over. So it's used for localization, telling you where you are. Mapping, which is trying to get a map of the world when your sensors are noisy. SLAM, which is basically doing localization and mapping. So telling both where you are and the map together. And just more generally solving things called POM-DPs, which are systems where you can't observe the state. Okay. So we'll go through an example early next class, but all right, that's Bayesian filter. See you Wednesday.
Yeah.
All right.